And we're back. This time we have Yonatan Berman with us, speaking about reallocating geometric Brownian motion. Quite a mouthful. If you want to brush up on the preliminaries, I recommend watching the Ergodicity TV video on random multiplicative growth. Yonatan joined the Ergodicity Economics program as an LML fellow in 2018, following a postdoctoral position at the Paris School of Economics. Apart from his full-time position at the London Mathematical Laboratory, he is also an affiliated researcher at the Stone Center on Socioeconomic Inequality in the City University of New York. He's also a fellow of the World Inequality Database Project. The model Yonatan will introduce is both very simple and very useful. With it, we can answer a fundamental question of stability, as he will explain. But I thought a few words on stability would be in order before we get started. There's a strong intuition, a very general one, which suggests that things are stable. The argument is this: something that exists can't be unstable because otherwise it would have fallen apart, and it wouldn't exist. This is in the vein of Lenz's law in electrodynamics, which says that an induced current will reduce the change in magnetic field that caused it. It's a stabilizing law. In chemistry, we have something similar, Le Chatelier's principle, somewhat more general. In equilibrium situations, the effect induced by a cause counteracts the cause. In other words, we don't expect to see positive feedback. When I lean against the wall and thereby cause a displacement of some of the atoms in the wall, I expect that displacement to cause a force pushing back against me. I don't expect the atoms in the wall to reinforce by pushing against them and in effect suck me into the wall. This intuition can be hard to shake off, but is not always valid. Walls can collapse. More subtly, I may be looking at a system and think, clearly this must be stable, although it is in the process of exploding. But the explosion takes place so slowly that I don't notice it's happening. Reallocating geometric Brownian motion can help answer this question. When we see economic change, is it because of fleeting fluctuations around an equilibrium? Is it because conditions have changed and we're settling into a new equilibrium? Or is it because things have started to come apart and we're witnessing, in effect, an explosion in slow motion? Maybe one last thing. When we started working on this study, we all had the same wrong intuition. We all believed we would find something stable, so much so that we spent a whole morning trying to debug a bit of code that was working perfectly well, perfectly fine, but produced results we couldn't make sense of. Until we took another look at the mathematics and found out that our gut feeling had simply been completely wrong. If this sounds intriguing, apart from listening to Yonatan, have a look at the video description below for a blog post and the paper we wrote on the subject. Enjoy the video, here comes Yonatan.
In today's video, I will take geometric Brownian motion as a starting point and then tweak it to make it a more realistic model for personal wealth. I will then use it to analyze real wealth distributions, how many people own how much, and the evolution of such distributions over time. We will see this for the United States and for India, and we'll find something surprising. I'll also explain how ergodicity is related to studying wealth inequality. In an earlier video, we saw random multiplicative growth and geometric Brownian motion. If we use that as a model for the wealth of individuals in an economy, it looks like this. At each time step, for example each month, everyone's wealth is multiplied by a random Gaussian distributed factor with some drift. Ergodicity was also discussed in an earlier video. In the context of a model for personal wealth, it would mean an equality between the long-time average wealth of each individual and wealth averaged across the population. In geometric Brownian motion, for example, wealth is not ergodic. Its time average is either zero or diverging, depending on whether single trajectories decay or grow over time. Its ensemble average is neither of those things. It is a positive quantity that depends on time. So the objects just cannot be the same. A standard trick, widely used by researchers who study wealth or income distributions, is dividing wealth by the average wealth at each moment. This new object is called rescale wealth, and the rescaling removes any non-ergodicity introduced by the simple fact that overall wealth might grow. In geometric Brownian motion, rescaling doesn't make wealth ergodic. The mean rescale wealth is always 1, but the distribution becomes more and more unequal over time. It never becomes stable. In the animation, we can see the distribution of rescaled wealth for a population in which everyone's wealth follows a geometric Brownian motion with the same parameters. We assume everyone starts with the same wealth, 1. Over time, while the average rescaled wealth remains 1, the distribution expands indefinitely, and inequality always increases. We can see that by looking at the threshold to be included in the top 1%. It increases with time indefinitely. Note that this is all in rescaled wealth, so that the average rescaled wealth in the population is always 1. So rescaled wealth in geometric Brownian motion is not ergodic, and its distribution never stabilizes. It seems that geometric Brownian motion is just not such a good model for wealth. What other model then? Geometric Brownian motion has the problem of the non-ergodicity of rescaled wealth. This seems unrealistic, but also we can't use it to test if rescaled wealth is truly ergodic or not with data. Most other models out there seem to have the opposite problem. They would treat rescaled wealth as ergodic or impose assumptions that guarantee it. We can tweak geometric Brownian motion by adding interactions between individuals. The interaction can take a form of a wealth reallocation term. This new model is called Reallocating Geometric Brownian Motion, or RGBM. It means that on top of random multiplicative growth, each individual contributes a fraction of their wealth every time period to a common pool. The pool is then split evenly between everyone. Mathematically, it looks like this. Quite similar to geometric Brownian motion, but with the addition of the reallocation mechanism. The magnitude of the reallocation is determined by a rate, denoted as tau in the equation. This model appears in various contexts. It was rediscovered independently several times by different groups studying economic inequality. It was studied in detail in the last couple of decades. Links are in the description below. The reallocation rate tau is assumed to be the same for everyone. The higher tau is, the higher the fraction of wealth contributed by each individual per unit time. With tau equals 0, we go back to geometric Brownian motion. With a positive reallocation rate, everyone with wealth that is above the population mean is a net contributor. They contribute to the common pool more than they receive from it. Everyone with wealth below the mean is a net receiver. With a negative reallocation rate, this is exactly the opposite. The reallocation rate can be interpreted as summarizing all interactions in an economy. It does not capture any specific policy. This is important for the interpretation of its value. So what happens to the wealth distribution in reallocating geometric Brownian motion? Specifically, are wealth or rescaled wealth ergodic? It turns out that the rescaled wealth is ergodic if the reallocation rate, tau, is above some threshold that depends on the model parameters. For large enough populations, for example a population of a country, this threshold is basically 0. So rescaled wealth is ergodic when tau is positive. When tau is negative, rescaled wealth is not ergodic. To summarize the last point, When tau is positive, this is an ergodic regime of reallocating geometric Brownian motion. The rescale wealth distribution converges in time. We can even derive the exact distribution it converges to. It's called the inverse gamma distribution. This distribution recovers some stylized facts about realistic wealth distributions, such as a Pareto tail. This is shown in this animation. This time, unlike in geometric Brownian motion, the distribution of rescale wealth converges over time. We can see that the threshold to be included in the top 1% reaches an asymptotic value. I will go back to the question of how quickly the distribution converges later. For negative tau, we have a non-ergodic regime of reallocating geometric Brownian motion. The rescale wealth distribution diverges, with some wealths becoming negative even if they all start positive. We can now look at data and ask what reallocation rate fits best to the data. Because in geometric Brownian motion we get an indefinitely growing inequality, it made sense to us that tau will be positive, perhaps a few % per year. This chart shows the results of such an estimation for the United States, done using wealth distribution data from the World Inequality Database. It shows first that the fitted tau values fluctuate over time and are not strictly positive or negative. A smooth series, shown in red, shows that the reallocation rate moved from being positive to negative several times over the past 100 years. In the past 40 years or so, it was consistently negative, between 0 to -2% per year. That was a surprise. Geometric Brownian motion already seemed like a wild and unrealistic model in which rescale wealth is always non-ergodic. But here we see that the picture is even more unstable than it would be for geometric Brownian motion over the past few decades. This wasn't a mistake. In fact, a somewhat similar result was recently found by Sahasranaman and Jensen for income in India. This result, which is robust for the United States when using the World Inequality Database data, means that the ergodicity of rescale wealth cannot be confirmed. In fact, the last few decades are characterized by a non-ergodic regime of reallocating geometric Brownian motion. In this regime, the wealth distribution diverges, and the reallocation is effectively from poorer to richer, and not as we thought we would find. The fitted reallocation rate series can be also used to derive the convergence time of the wealth distribution to its asymptotic form in the case tau is positive. Convergence means that over time the wealth distribution approaches the steady-state distribution, and the distance between them decays over time. This decay has a characteristic timescale, which depends on the reallocation rate tau. The higher tau is, meaning more reallocation, the shorter this time is. This also means there is more wealth mobility, but we will talk about it some other time. This chart shows the convergence times for the smooth reallocation rate series shown before for the United States. In many cases, convergence is not possible because tau is negative. When it is positive, the convergence times are generally between 20 to 150 years. So, we have either negative reallocation, giving from pool to reach, or we have timescales that are decades or centuries long. The effects of policies aren't in the data for years. This analysis shows that assuming ergodicity when studying models aimed at understanding wealth distributions and their dynamics is unwarranted. It's also a demonstration of how useful reallocating geometric Brownian motion can be for addressing other topics, such as wealth and income mobility. In the description below, you can find links to several papers from the past few years studying different properties of reallocating geometric Brownian motion and various applications. This is enough for today. Thank you so much for watching, and I hope you have a great day.